Pop quiz. Which substance can form hydrogen bonds with itself? Sodium chloride, hydrogen chloride, ammonia, or methane? Lock in your answer. We will reveal it soon. And by the end of this video, you will know exactly how to spot it fast. In this video, you will learn what intermolecular forces are, how to tell the major types apart, and how related ion attractions fit into the same pattern. We will also build a quick ranking system you can use on chemistry questions. First, a key distinction. Intramolecular bonds hold atoms together inside a particle. Intermolecular forces and closely related particle attractions act between separate particles. Most molecular intermolecular forces are weaker than covalent or ionic bonds, but they strongly affect melting point, boiling point, solubility, and physical state. Here's the big picture. As a general guide, stronger charge differences usually make stronger attractions. Ion-ion interactions are very strong because they involve full charges. Ion-dipole attractions are also strong. Among molecular forces, hydrogen bonding is usually stronger than ordinary dipole-dipole. London dispersion forces happen in every substance, and they can become much stronger in larger or more polarizable particles. Ion-ion interactions happen between particles with full positive and negative charges. In an ionic solid, those attractions extend through a crystal lattice. That is why many ionic compounds are hard, organized, and have high melting points. Ion-dipole interactions happen when an ion is attracted to the partially charged end of a polar molecule. For example, when calcium chloride dissolves in water, the water molecules turn to line up their negative side toward calcium ions and their positive side toward chloride ions. Those attractions help pull the ions apart and keep them surrounded in solution. Dipole-dipole interactions happen between polar molecules. Each molecule has one end that is a little more negative and another end that is a little more positive, so they line up attractively. A special, stronger case is hydrogen bonding. This happens when hydrogen is bonded to nitrogen, oxygen, or fluorine, and is attracted to a lone pair on nitrogen, oxygen, or fluorine in a nearby molecule. Let us answer the pop quiz. The correct choice is ammonia. Ammonia can form hydrogen bonds with itself because it has NH bonds and a lone pair on nitrogen. Hydrogen chloride is polar, but it does not count as hydrogen bonding under the usual general chemistry rule. Methane is nonpolar, and sodium chloride is ionic rather than a hydrogen bonding molecular substance. Here is a common mistake. A molecule can have polar bonds and still be nonpolar overall if the geometry cancels the dipoles. Carbon dioxide is the classic example. Its bonds are polar, but the molecule is linear, so the dipoles cancel. Sulfur dioxide is bent, so its dipoles do not cancel, and it is polar. So far, we have covered the main pattern. Full charges give ion-ion attractions. Ions with polar molecules give ion-dipole attractions. Polar molecules can have dipole-dipole forces, and when hydrogen is bonded to nitrogen, oxygen, or fluorine, and is attracted to a nearby lone pair, it can form a special, stronger attraction called hydrogen bonding. Want to lock this in? Your personalized practice test and flashcard set are all waiting for you. Tap the link and give yourself a quick check. Now for the force that every substance has. London dispersion. Electrons are always moving, so at any instant, one side of a particle can become slightly more negative than the other. That temporary imbalance can induce a dipole in a nearby particle, creating a brief attraction. It is weak for small particles, but it can add up in larger ones. This is why larger non-polar molecules can still stick together surprisingly well. Methane is small and has weak dispersion forces, so it is a gas at room temperature. Hexane is larger, so its dispersion forces are stronger, and it is a liquid. Very large hydrocarbons, like those in candle wax, have even more surface area and more electrons, so dispersion forces can become strong enough to help make them solids. Another common error is thinking a substance gets only one attractive force. In reality, dispersion is present whenever particles have electrons, but it may not be the strongest force. For ionic compounds like potassium bromide, ion-ion attractions dominate. A polar molecule like acetone has dipole-dipole and dispersion. A nonpolar molecule like bromine mainly has dispersion. A substance with hydrogen bonding also still has dispersion. Here is the fast method. First, check whether ions are present. If ions are attracting other ions, think ion-ion. If an ion is interacting with a polar molecule, think ion-dipole. Next, if the substance is molecular, ask whether the molecule is polar. If it is polar, it has dipole-dipole forces. Then check whether hydrogen is bonded to nitrogen, oxygen, or fluorine and can be attracted to a nearby lone pair. That is the key pattern for hydrogen bonding. Finally, remember that every substance also has London dispersion forces. To recap, intermolecular forces and related particle attractions act between separate particles. The main clues are ions, molecular polarity, hydrogen bonding, and particle size. Full charges usually give the strongest attractions. Hydrogen bonding is a strong special case, and London dispersion is always present, becoming more important in larger or more polarizable particles. Ready to quiz yourself with the content covered in this video? Check out the link in the description, where you'll find Quizlet content made just for you.